right. Hi, everyone. Thanks for joining our Crunch seminar this week. So this week we have two speakers. The first one is Celik. He is a postdoc in our Crunch group, and he received his PhD in applied math at Donquds Elu University in Turkey. Jem is going to give us a talk entitled Physics Informed Neural Networks for Elliptic Elliptic PDEs on 3D Manifolds. So please join me and welcome our first speaker.
Thanks for the introduction. Yeah, I think I shared my screen, right?
Yeah. We can see you.
Okay. Hi, everyone. I'm going to present you a paper review titled Physics Informed Neural Networks for Elliptic PDEs on 3D Manifolds, which is written by these authors and submitted to computers and mathematics with applications. Here is the outline of the paper, which is a very short paper. They considered a second order elliptic surface PDEs on 3D manifolds. A combination of surface gradient and Laplace-Beltrami operator used in the PDEs with different manifolds. Pins are applied to approximate solutions, and they give some numerical results. The definition of the partial differential equation is in that form. Here we have delta S. Here delta S is the Laplace-Beltrami operator. Nabla S is the surface gradient. A, B, C are constants. They consider the D equal to 3 case, 3D case. And B is a vector, and A and C are scalar constants. These type of equations are used in generation of textures on surface, like we have in this first picture. Visualization of vector fields, like we have here in the bunnies. There are vector fields here, different type of different types. Image processing and flows and solidification on surface in fluid dynamics, like I have here an icing simulation on a surface. This is surface. The definition of the surface gradient operator is in this form. This is the regular gradient operator, regular Euclidean gradient operator, and the n is the unit normal, outward unit normal vector at any point of the surface, and the I is the identity matrix. Using this gradient, surface gradient operator, we can define the Laplace-Beltrami operator as in this form. This is the same form as we have in regular Laplacian. Instead of the regular gradients, we have here surface gradients. So Laplace-Beltrami operator, sometimes called surface Laplacian. The authors are considered these representations instead of using direct calculation, using direct definition. Here, these representations are given in that article, and we have surface gradient operator is defined by regular gradient operator and extra term. A surface Laplacian operator is defined by a regular Laplacian and extra terms. The first term here is Again, this is the unit normal vector, and this is defined by here, and it's just a directional derivative in the direction of normal. And in the second term here, the HS is a trace of a matrix, which is a multiplication of two matrices. Here we have a Jacobian of the normal vector, and this matrix is the same matrix as we have in the definition of surface gradient. Then they give an example. As an example, they choose unit sphere as a surface, and in this unit sphere, we have this easy normal vector for any point, and they give the results for the surface gradient in that form, and for the Laplace-Beltrame operator in that form. The result for surface gradient operator is correct, but this result for the surface Laplacian is not correct. We can check here. I think what they did wrong here is taking regular gradient of applying the regular Euclidean gradient to this gradient, because if you take the partial derivative with respect to x of first row, you'll get this term, this first term, this one of these terms, and the last term from the first row. And if you apply for these to the other rows, you'll get exactly this. So they calculated this wrong. I calculated by using the regular definition like this one, and I found this result for the Laplace-Beltrame operator. And to verify my results, I find another representation which is given by these authors, and I also calculated this, and I get the same result. So the correct Laplace-Beltrame operator for the sphere, unit sphere, should be in this form. Then they applied pins to the equation. Since they are always using closed manifolds like sphere or closed surface, closed another surface, they don't have any boundary conditions. They only have the residual of the function as a loss function, as a loss of pins, and they use the same representation, the same operator representations here in the loss term. And they considered 6 different manifolds, 6 different surfaces in the equation and applied pins to them. They used Xavier initialization and LBFGS methods. Then they give directly the numerical examples. As a first example, they considered the unit sphere again. And as a constant, they consider here A1, B vector 1, 1, 1, and the C vector as 5. Then they take this function as a reference function, then they generate the first term using this reference function. Then they give some results. Here they calculated the L2 error. This is actually relative L2 error. And then they write here the number of training data, but I think this is wrong. It should be number of epochs or something like this. It doesn't seem to be the number of training data to me. And they say these results are the mean of 10 different runs. In the first graph, they fix the depth of network and change the width of network. The results look similar. In the second example, in the second graph, they fix the width of network and change the depth of network, and the looks are again the results are looks similar. As a training data, in total they use 2500 quasi-uniform points, which are generated by using minimum energy method. I look for the minimum energy method on the internet, and I found an article which describes how to generate this. What they did, they actually divide surface into rectangles, which they call surface rectangles, like they have here. And in each rectangle, they have a parametrization which only depends on the angles of the points on these rectangles, like we have in the spherical coordinates theta and phi. And they choose in each rectangle, they choose points using that parametrization. Then they give some other examples for some other results for the numerical these examples. In first plot, they say it's numerical errors. I assumed it as a numerical absolute value of the error. In first graph, they used all the data, all the generated data as a training data. We don't know if they use test points or not. They didn't tell anything about it. In the second one, in the second graph, they used 1500, and here 100, and the last one they used just 10. First two, the errors look same. The biggest error is the 10 to the minus power 5 here in first two examples, and here is a little bit higher, and here for the last one they got better results. I don't know why they tried for 10 training data, and all these examples they used 3 hidden layers and 50 neurons as a network structure. And then they consider 5 more surface as a second example, which includes torus, constant distance product, and something called Brescia-2, orthocircle, red blood cell. And they considered this function as a reference solution, and they generate first term using this function. Only difference here is the second term. In the first example, they have seen y here. I don't know why they changed here, because there is no explanation about it. And here again, they used the same parameters for A and B, same constants for A and B, and they changed the last one. This is again, this was 5 in the first example. Here is 1. I don't know why they changed these. And as a network structure, they use 3 hidden layers and 50 neurons. For all examples, number of epochs are not known. And we don't have any loss graphs also for the examples for the rest of examples. They give numerical results for the torus example. In the torus example, they choose 500 quest uniform and 500 randomly selected points. And if we don't know if they use any test points or not, the results look same. The errors look same. And then they jump the other examples. Here they take 500 training data. This time they consider to give all the total number of points which considered for each example. Like in the first example, they take this much points. I don't know how they decide to take the points. That they didn't give any information about these also. But they take 500 training points, and the rest of them as a test points. They tell this in their article, and the results, the errors looks nice, I think. Then they give some relative L2 errors for the last 4 examples. I think they forgot to give the relative L2 errors about the torus example, and relative L2 errors seems okay to me. And that's all they have in the paper. I write all the things here, and as a result, as a summary, they claim they use pins as a first attempt of surface PDs on manifolds, which we don't know because they didn't give a lot information about this. They just put some graphs of some errors which we don't know. They should give more loss graphs or another things to convince the readers or reviewers. And Laplace spectrum operator is not correctly calculated. And I don't know, maybe they should give some common examples which are considered before in the literature, and they should compare their results with them, which they don't give us. That's all they have.
Cem, is this a paper I asked you to review?
Yes.
Which journal? Do you remember?
Yeah. The computers and mathematics with applications.
Oh, okay. Yeah. So
besides that, they have also a lot of errors in the paper which I corrected when I'm writing here.
Right. So you're convinced that there are Laplace-Beltrami operators wrong, right? I mean, you demonstrate that, yeah.
Yeah. Because we can check here. They calculated it wrong. They applied the regular gradient to the surface gradient. So this calculation is obviously wrong. Yeah, this should be something like this. And I check my results with another representation. I write a small script on computer and I check all the results.
Yeah, okay. So basically all the results are wrong then?
I assume that because they didn't tell a lot of information about how they calculated the rest of the surface, because they only give us the first one, and the first one is wrong. If they use same computer routine to calculate all the examples, they should be wrong. Yes, it should be wrong.
That's terrible.
Yeah, that's terrible. Since they are using fabricated first term, pins, of course, pins should approximate, should converge a function. And
but I think the L2 errors are with respect to the data because they want to show convergence.
Yeah, it converges, yeah.
Yeah. So they want to show convergence, but converge to the wrong answer because the reference is wrong if they have their so everything.
Yeah. Force function are wrong because
That's unfortunate because the PDEs on 3D manifolds is really interesting application. Like you show the red blood cell.
Yeah, the first, this one also good, and they have also biology examples which I couldn't find so good pictures to represent you, but they also have examples on biology too.
Okay, is there any other questions for our speaker?
Excuse me, can I ask you a question?
Yeah, of course. Sure.
This is Ting Wei. Actually, this work reminds me of some of my master works. Although I didn't do that for a long time, but at that time we are solving also some PDEs related to the Laplace Beltrami operator on some manifold. The application may be on the brain structure and some medical data like that. I don't know if I haven't followed this direction for a long time, but I don't know if there are some people doing neural networks solving that kind of like mapping between different surfaces, like brain surfaces or face of different people, those kind of 3D structures. I'm just curious about.
Yeah. I also wonder about this, and I look for the internet. Their claim is correct. They applied neural networks, or actually pins, to that kind of PDEs as a first attempt. I couldn't find another attempt to an application of neural networks of these type of 3D manifolds. This is first attempt, but I think since their calculation of the operator is wrong, all these results are wrong.
I see. Okay, thank you.
Any other questions?
An interesting problem would be to have evolving. So this surface is evolving, like for example, the red blood cell, how the red blood cell deforms. So it would be, and the question is then, how do you go from one time instant to the next, right? If you can do transfer learning or something like that, and maybe then it will be in, you can include time explicitly, I mean, in discrete time or continuous time, and see how the surfaces are evolving. I think also the same thing for solidification that you had here.
Actually, these two solidification examples and these bunnies are have time included. In the bunny example, this is earlier time step, and this is the last time step. The second one is the later time step. This first one is the earlier time step, which they show how the vector field changing in time in that particle.
So what is? Can you go back to the equation? What needs to be changing for this surface to be evolving?
This is not the exact equation. In this example, they used Laplace Beltrami operator and the surface gradient, and they added a time, like we have in diffusion examples. First order of time.
Oh, I see.
Yeah. These equations are parabolic equations.
Okay. So parabolic. Okay, okay, got it. Yeah. So that makes it relatively easy to represent evolving surfaces. So maybe Cem, maybe you can do a project like that on like including fluids for interfaces, evolving interfaces in fluids.
Yeah.
Which are driven by capillary forces, that are driven by shear stresses, are driven by pressure. Of course, 3D, so then you have full surface and see how we can track those surfaces different with particle methods and other methods, but this could be a interesting project to look into.
Yeah. It looks interesting to me too.
I have just a quick comments on that. So it reminds me like the work of one of the professor in BME, biomedical engineering at Brown. So basically I've listened so Professor Ian Wan in BME. So they basically model the cell migration by using this 3D PDEs on 3D manifolds. So the cell migration can be described by this some PDEs on 3D manifolds, and then they basically so the 3D manifold could be a network structure that are fibrillar networks, and so the cell can migrate on that on this network and be transported to another location. So I think that it is a very interesting topics in biology.
Yeah. They have a lot of examples. I saw a lot of examples articles, including biology, but I couldn't find a good picture to present you as an example of these type of equations.
Yeah. Okay. If there's no more questions, so please join me and welcome. Thanks our speaker again. So our next speaker is Yeonjong. Yeonjong is a Prager professor at Brown. So today, Yeonjong is going to give us a presentation with title, A Caputo Fractional Derivative-Based Algorithm for Optimization. So please join me and welcome our second speaker.
Thank you. Could you allow me to share my screen?
I already make you as co-host. Is that okay? Yeah. Okay. Yeah.
Thank you. Okay. Can you hear me well?
Yep.
Okay. So let me see. All right. So today I was going to talk about, by the way, thank you for a nice introduction. And today I was going to talk about my recent work with Jerome and George, the Caputo fractional derivative based method for optimization. So the goal of the problem is to solve this minimization problem, unconstrained one. Here, f is a real valued function defined on d-dimensional space. And we assume f is sufficiently smooth enough to the purpose of defining Caputo fractional derivative. So the standard scheme, I think not standard, but the most fundamental scheme for achieve this goal is to run gradient descent. And gradient descent is written in this simple manner, just an iterative scheme by using gradient. Then in the first place, why we want to use the gradient? And this could be just optimization 101, but it is based on the linearization principle. So we can approximate our objective function at around current point linearly. Then the right-hand side you're seeing is just a first order approximation of the right-hand side, or you can think of the truncated version of the Taylor expansion with respect to xk, which is our current point. Then it can be seen that the right-hand side is minimized if we set x minus xk to be negative direction of our gradient, and eta is somehow the step size. Then if this is the case, then the right-hand side, the second term becomes the minus eta and the square of the gradient, norm of the gradient square. Then this will give you the gradient descent. And the step size can be found by applying the minimization rule, which is just a one-dimensional minimization problem. And it is well known that the rate of the convergence depends on the condition number if you are solving quadratic problem. And these are all belongs to classical optimization 101. And this is some geometric interpretation, how gradient descent work, so that if you have started at here, then we just create a linear approximation here. Then we just trying to minimize along the manner. So we have a clean explanation, and we have geometric interpretation of GD, so that GD is well understood. However, we know that GD often suffer from some local minimum. And to be honest, when we train neural network, we don't really use gradient descent, rather we use some variant of it. So this is some definition to attempt to define the Caputo fractional derivative. So that this, I'm here just showing the standard gradient and how it is defined. And this will be used in a way that when we define the fractional gradient. So first of all, I will just distinguish the two things. The one is the derivative versus the gradient. So derivative is just a notion of the derivative in unit, that's one single variable, and gradient is a generalization. So unlike this, the standard integer order derivative and gradient, actually, we don't have its corresponding counterpart. But let me first show you what is the Caputo fractional derivative, so that this is the definition, so that it is often neglected that Caputo derivative has two definitions. One is the left and the other is the right, and depending on how you choose this integral terminal. So here alpha is the fractional order, which goes to here. And C here, let me focus on the left definition. And C is called the left integral terminal. And this C defines this lower integral part. So this C is called the integral terminal. And the gamma is just a standard gamma function. And we have x minus t, so that making sure that this quantity is always positive because we have exponent alpha, unless you're gonna get the complex number. And right definition is also defined in similar manner, but x now belongs to smaller than b, so that it is quite important that when you define in Caputo fractional derivative is whether you are evaluating at from the left or from the right. And the same principle applies, but you have the minus sign here up front, and integral terminal appears on the above, and making sure that the parenthesis always being positive, so that t minus x. So these are just the definition of how Caputo fractional derivative are defined. But I will going to just use this left notation, even though regardless of how c is smaller than x or greater than x, I will just, if that is the case, then you can interpret it as the left Caputo fractional derivative. So that will, from now on, I will going to focusing on this notion and implying both two. And the motivation is the following. All right, we have integer order derivative. Then from the integer order derivative, which is here, integer order derivative, and we get the gradient, and we can get a gradient descent. Then naturally, we have fractional derivative. Then somehow we can define, if we can somehow define fractional gradient, then we can use fractional gradient descent. Then this is a naive motivation. And from this motivation, many people have proposed so-called fractional gradient descent as a generalization to integer order gradient descent. And some of the work have actually proposed a variant of the method and have represented some promising empirical result, but the mechanism behind the fractional gradient descent, or what do we mean by fractional gradient, is not well investigated in a sense. So let me first, before I show our proposed method, let me first define what we mean by Caputo fractional gradient. So first of all, we need to have a function, real valued function, and x is a d-dimensional point, and c is also a vector lies in d-dimensional thing. And you can think of the c is the integral terminal I will going to use for this purpose. So c here or b, depending on size of your location of x. And since the Caputo fractional derivative defined on real valued function, we need to have real valued function. So we define a real valued function, a set of real valued function like here. And this is nothing but for fixed x. So you can think of x is a constant. Now our variable is y. Then you can think of this is just, we are just treated this in terms of changing j's component. Here, ej is a standard unit, standard basis vector. Then this is a real valued function. Then we have 1 through j. So d real valued function defined on R. So now we can apply the fractional Caputo derivative and get Caputo fractional gradient. So each of the component is actually the real valued function defined on R. And we just applying the Caputo fractional derivative like component wise. So this is our notion of the Caputo fractional gradient. And of course, this can be more generally defined if you have some specific coordinate in your mind, then you can easily replace this standard basis vector to whatever coordinate you have in your mind. And as you can see, this is a natural extension to the Caputo fractional derivative with respect to Cartesian coordinate. And as I show you here before, then this is how the standard gradient is defined, and with respect to h and e1, and this is the analog of how I define this Caputo fractional gradient. All right, then with this the gradient fractional gradient is defined, then vanilla Caputo fractional gradient may be written in the following manner. And here's the one note. And in general, the Caputo the stationary point of Caputo fractional gradient is not the same as the stationary point of the integer order gradient. And this is something I need to mention. Then with that, now we are ready to present our proposed method, Caputo fractional gradient descent. Starting from initial point x0, for every iteration, we need to choose 3 parameters. So this is a generic version. So once you identify what kind of alpha, beta, ck to be used, then you get a specific version of the Caputo fractional gradient descent. But this is a generic version. So you have a choice, and you update your current solution according to this. So this is just our current position, and eta k is the step size, and dk and vector, this is a direction, is defined as follow. So first of all, we have a one scaling factor here, diagonal and inverse. And here is some notation. So diagonal Vj means that this is diagonal matrix whose component goes like this. And you take inverse, then this is one of our component. And we have some sort of like scaling here. And you see that we have Caputo fractional gradient with respect to x, and its order goes like alpha k and 1 plus alpha k. And you see that we have a beta k here and diagonal scaling as well, which is the difference between the current point and our integral terminal. Then this is, I said, this is a generic Caputo fractional gradient descent, and you need to choose the 3 things: the fractional orders, smoothing parameter beta, and ck. And you may wonder where this direction comes from out of nowhere, because you can see that comparing to the vanilla Caputo fractional gradient, actually this is somewhat coming out of nowhere. But here is the motivation and where this formula comes from. And this is one theorem we found is the following. So I want you to focus on just this function only first. This function looks like a tail expansion of f at c point. And if you think about this ck alpha beta to be 1, then this is exactly the tail expansion. However, this CK alpha beta is defined as here, so that this controls some of the smoothings. So that how you choose the alpha, which is the fractional order, and beta, as I said, beta is a smoothing parameter. And depending on these choices, actually, you can define a new function, which is a smoothing of the original function. And as a result, what you get is actually, when you actually think about this is your objective function and applying the gradient descent, and this is the direction you're gonna get. So this is the steepest descent direction of our smoothing at x. Then you can see that naturally Caputo fractional derivative is sure rise. And you can see that this is look alike what I have defined in the previous slide. So this is the general d-dimensional case, and this is just a univariate version of it. And note that when alpha equal to 1 and beta equal to 0, then what you get is the CK10 is just 1, which means that our smoothing is just an original function. Then you're recovering gradient descent, standard gradient descent. So in a simple word, how this fractional Caputo derivative arise is actually come from the smoothing, specific type of the smoothing of the original target function. Then this somehow justifies why we want to use the fractional derivative towards to minimizing objective function. Is there any question at the moment? Okay, then let me continue. So this is some illustration of what I have said. So here our f, suppose you can imagine this is our target function, f, which is shown as the black solid line here. And here I set the alpha equal to 0.66 and beta is 1.0. And blue solid line indicating our smoothing function. And if we choose the specific point, let's say x equal to 0.7 here, then at this moment, you can think of the linear approximation. Then this green line indicates the linear approximation of original objective function. And the red line is the linear approximation of the smoothed objective function. Then this is the red line indicates the fractional Caputo derivative direction that we just did, that I just show you. And C is the reference, the point, which is the integral terminal. Okay, then with that, now we have some of the interpretation and the intuition and how we get this type of the direction related to the Caputo fractional derivative.
Yeonjong, maybe you can give a reference to the theorem, to the expansion that you had before.
Here?
Yeah. Yeah, this one. Where did you find this?
Okay, so this is a good question. So to be honest, I come up with this formula from the analysis. So we started this project a year ago during the summer, one meeting, and Jerome and I and George and thought about how we can incorporate the fractional derivative into the optimization. And I analyzed a very simple case, and turns out that fractional derivative actually is not a good idea. If you strictly use this naive formulation here, I figured that out. Actually, this doesn't help at all, actually produce the worst result. And my analysis actually indicates that, but if we add one more extra term like this, actually this term, actually we can do a lot better. Then I extended that idea and find out this exotic expansion form, specific smoothing form.
Right. So it's not from Maynard's book. It's not like a standard in the fractional literature. That's why I wanted to basically say that. Yeah. Okay.
Yeah, that's probably why that must be the case, because it's somehow theory-driven expansion. Yeah. So, okay. Then one of the question for the fractional Caputo derivative, actually, when I first encountered this equation, my first question was, besides whether it works or not, how we compute the Caputo fractional derivative. So here is the answer. So we figure out explicit formula how we compute the Caputo fractional derivative. So this is quite little technical details involved, but let me focusing on this. So this involves integral, one-dimensional integral, which integral from -1 to 1, and we have such a function here, and 1 minus u and minus power of minus alpha du. Then this is actually, we have a really good method to estimating it. This is a Gauss-Jacobi quadrature. So in the implementation level, we can actually employ the Gauss-Jacobi quadrature using, so say, S point. Then this will give you the following formula. Then you may want to ask then, all right, then compare to gradient descent and how expensive this is. And roughly speaking, cost of GD times the number of the quadrature point you used is roughly the cost of the Caputo fractional gradient descent. So in fair comparison, we better to perform better than GD, the number of quadrature times when you fairly want to compare the performance versus the computational cost. And I will show you the result in more details, but we wins by large margin.
Yeonjong, here the 1 minus u, that's the weight in the Jacobi, right?
Yes.
Okay. So naturally it's absorbed because of the way you do the Jacobi integration. Okay, good.
Yeah. So those 1 minus u to the minus alpha actually observed in this weight WL, which is the predefined Jacobi quadrature. Yeah.
Can I ask a quick question here, Yeonjong?
Yeah, go ahead.
This is Hassan. So this d sub k that you're computing, it's that directional derivative, the fractional derivative, right? So how come the bounds of the integral that you have are constant and fixed?
So it's a J's component. So dk is a vector, and I'm just asking J's component. So which is the constant, right?
Okay, so but are you computing a fractional derivative here or not?
Yes, fractionally. So dk bar is coming from. Okay, let me rather show you next slide. So this one, I'm computing this dk bar.
Okay, so I see that, like, for example, in the gradient that you have, so it goes from c sub k to x, right? So then in the integral of the fractional Caputo that you have, so the bounds of the integrals should be from ck to x, right? But do you do like a mapping to map it from your domain into -1 to 1?
Yes, so that's why it is a theorem rather than proposition, so that we have some change of the variables and go some derivation so that you can actually incorporate this bound to be ±1. But you're right. So if you just write it out directly how it is computed, then you will not get this formula. But you do better to some change of variables, some tricks, and then you will eventually able to get this formula. Then you have a little constant out here, right? So that is the constants of the normalization.
Okay, I see.
Yeah, that's a good point. Yeah, that's a good point.
So it's a linear mapping, right? CK to X, and you map it to -1 to 1. I think that's what Hassan is asking.
Yes, and I'm wondering, so when I'm not sure if there is any notion of time, like, or iteration that you have in the X, but if there is, so when the number of iteration increases, so basically the domain over which you are computing the fractional gradient increases, right? So ck to x. I'm not sure if I completely understand like the concept of fractional derivative here, but if there is any inherent time, which is the iteration of the optimization. So as the number of iteration grows, then you have a larger domain over which you are
Right, you're right. You're right. That is
right?
reflected in this situation. So if you look at this delta, then
Okay.
actually this is the distance between your reference the terminal, the integral terminal, to the point where you are evaluating it. And this is the divided by 2, and also actually you have 1 plus u, which is varies plus and minus 1, so that it varies the 0 to 2, so that when it multiply to here, actually you are integrating the domain from Cj to xk, so that is all considered in this formula. Does that make sense?
And do you have to adjust your number of quadrature points as you increase?
No, just fixed. This is a fixed quadrature point. I mean, this is just the integral form, so that, but you may be right, but in implementation level, we don't adjust the number of the quadrature point as the iteration goes by. We just fix the quadrature and run it.
Yeah. Because
actually, Akshan is proposing something that we haven't done yet. Maybe Yeonjong is, and you could show the results later. But maybe you know, you will start with the initially with low s, low value of s, then increase it at the end. Although, and if you will show robustness and so on, I don't want to reveal your results, but that's not a bad idea to try that.
Yeah, definitely. Yeah, I like that idea. So that
variable s, because that's yeah. Because we know in the beginning if we are far away, right? Just use very low value of s, and then as you zoom in, you can refine your. So anyway, that's like there's no reason for s to be fixed, I think.
Exactly.
So you can use it to your advantage, John. I think that's what the son suggests.
And I think it's going to help with the computational cost that you have.
Yeah, definitely.
Because
that's actually a good idea. So
yeah. The Caputo derivative, I mean, any fractional derivative, you always have the bottleneck of the computational cost. So yeah.
I think it might depending on how you choose your reference the terminal. So what I'm expecting is that if you have some physical meaning, some designated the integral terminal, so that if it is the case whether this delta term might happen to grow very large as the iteration goes on, then this means that even though we are integrating from -1 to 1, the actual domain we are considering can be very large. If that is the case, then I think the more the quadrature point might help. I think definitely help in certain, also depending on what kind of function you have. But if the function is moving quite dramatically during that interval, then the more the quadrature certainly help. But I will show you in a moment that, because I didn't introduce you the 3 versions of the generic formula, but the generic formula actually somehow ensure that this difference is not too large, because the CK would be the previous iteration of the X, so that I think that wouldn't be a big issue in the framework I'm presenting right now.
Okay, I see. So your lower terminal is the previous value.
Iteration. Yeah.
Okay, all right. Okay.
That makes sense.
An increasing domain as you iterate more. Okay, I see. Makes sense. Yeah, thank you.
Yeah, that's a very, very good point. But as you mentioned, that if you need to fix the integral terminal, that might be depending on some constraint of the problem or physical quantities, then definitely that must be a good scheme. Yeah. So, okay, so this is the proposed method. Then as I said, we need to choose the 3 things: the fractional order, smoothing parameters, and integral terminals. So for that purposes, we propose the 3 versions. First one is a non-adaptive, so which is basically everything is constant and see what's happening. And the next one is the adaptive terminal. Everything is fixed but the integral terminal. So we are going to choose some previous iterations of our solution. So mainly I choose the L equal to 1, which is our previous iteration, to be our integral terminal, and adaptive order. So I will not going to talk about adaptive order today because I don't, because of various of reasons, but we did some analysis, but we don't have a specific method that advantage can be demonstrated. So I will going to focusing on these two methods. So convergence analysis focusing on the quadratic functions. So basically, I want to minimize this this function, and also this is a special case. Become the linear regression problem can be a special case of this. And if this is the case, actually we don't really need to go over the quadrature formula. Actually, we have an explicit formula. The exact formula can be implemented almost with no additional cost. And the interesting part is when we try to solve this quadratic minimization, actually the fractional order and smoothing parameter beta depends only through this gamma parameter. This gamma is defined in this manner, so that I will going to show the result in terms of gamma without specifying what is the fractional order or smoothing parameter. So for the least square problem, all that matter is to relation of alpha and beta, which is the gamma here. So in this case, we know exact what is the D, the Caputo fractional gradient descent direction, so that no cost or no approximation is employed. And for the next theorem, I need to just briefly talk about the Tikhonov regularization. So this is just the regularization problem that is very popular in the inverse community and image processing and etc. And its explicit solution is known to be here. And optimal step size in this case may be found by applying the minimization principle. And the first order condition will give you the following step size. And this is the optimal, so that we're going to use the optimal step size unless otherwise stated. All right, then here's our theorem. And this is quite hard to read at this moment, but let me focusing on this. So xk is the case iteration of our algorithm. And this Tikhonov star is the solution to the Tikhonov regularization. And this decays to 0 exponentially fast with the rate depending on the condition number of this A tilde matrix. And A tilde matrix depending on our smoothing parameter beta and the fractional order beta, alpha. So this indicates that non-adaptive Caputo fractional gradient descent does not minimize our objective function, but it converges to something which is the well-known Tikhonov regularization with a specific regularization matrix and the initial point. And this initial point, the reference point x bar actually becomes to our terminal, integral terminal. And let me show you how this looks like in the numerically. So here I show the L2 distance to the stationary point. And let me briefly mention that in a special case where gamma equal to zero, then actually this becomes the gradient descent. So everything is the same as the before gradient descent. So let me just point out. So when you set the gamma equal to 0, then direction is just the ax plus b, which is the gradient direction. So when gamma equal to 0, you can think of GD result is the case where gamma equal to 0. So here I show this L2 distance to the stationary point. Basically, I'm showing the result of this red box. Then you can see that depending on the gammas, actually we see the exponential convergence to their stationary point. But this does not mean that we are minimizing our loss function, objective function. So here I show the objective function values versus the number of iteration. You can see that despite of all these methods already converged to already achieved to their stationary point, they are not minimizing objective function. So with this observation, but nothing is wrong. Everything is as expected by theory. But sometimes we want to, in practice, we want to find a stationary point of the original objective function. With that goal in mind, we propose the adaptive scheme. So two adaptive scheme is proven to be converges to the stationary point with of the original objective function, which is the A inverse times B minus. And the adaptive terminal is setting alpha and beta to be a constant, and the integral terminal to be the previous iteration. And this is our error bound. And the interesting part is that this, depending on some type of the sequence of the matrices, which is defined through this type of the discrete matrix dynamics. And we are not able to show certain specific conditions under which whether this AK norm of the AK matrix goes to 0. But if this is the case, then convergence can be achieved. But this is the error analysis we derived, although there's more improvement can be done in this direction. And currently you are working on it and have some result on it. But let me show how powerful this algorithm is, this adaptive terminal fractional gradient, Caputo fractional gradient descent. So this is the simplest example one can think of. This is our two-dimensional optimization problem. And here we compared with the gradient descent versus our adaptive terminal Caputo fractional gradient descent. You can see that gradient descent do a great job in minimizing this objective function and its rate of convergence depending on its condition number. And if you see the adaptive terminal Caputo fractional gradient descent, in the first few iterations, 1 or 2, actually doesn't seem to decrease too much. But from the third iteration, it starts to decrease, and fourth iteration, it finds the solution exactly. So you can see that this is the loss value trajectory versus the number of iteration. Within merely 4 iterations, this adaptive terminal fractional gradient descent can find the optimal within machine accuracy, while gradient descent take a while to get the minimum, although it do a good job in finding a minimum, but requires more number of iterations.
Yeonjong, what happens if 10 instead of in front of x squared is actually 1,000?
Story does not change, and GD takes a more longer time, and our method still works.
But you know what I'm asking, right?
Yeah, the example is coming of the condition number is 10 to the 9.
Yeah, exactly.
The example follows up.
Right.
As George bringing that up, so this is the UCI machine learning data. So this is a real data, not just a random data. It's the largest data in their machine learning repository, and it's called the gas sensor array drift at different concentrations. And this is just a regression data. So the goal is to find a minimizer of this W transpose X minus Y, and W and Y are from their data. And it turns out this is really, really ill conditioned. So condition number is 10 to the 9. And here I show the gradient descent result with the optimal learning rate. It's a dashed line here. You see that the 10 to the 5 iteration is not enough to see the significant decay. But by using our method, adaptive terminal Caputo fractional gradient descent can effectively decrease the loss, and within merely 10 to the 3 to the 5, 10 to the 5 iteration, it already reached the 10 to the minus 5 distance to the stationary point. So this is the distance to the stationary point, not just the loss value. And similar thing observed for various type of the gammas, so that I plot each and every gammas from -20 through -81. And similar results are observed. So this is the huge significant improvement over gradient descent, which is by nature suffer from the ill conditioned number of the problem matrix. However, from these examples, indicates that our proposed adaptive terminal Caputo fractional gradient descent can effectively mitigate the dependence on the condition number of the problem. Okay. And we apply our methods to functional approximation using neural network case.
John, can I just if I was doing conjugate gradients, for example, right? The number of iterations would go as the square root of the condition number. So it would be like 10 to the 4.5, which is 10 to the 5th, which is here. Right? So a conjugate gradient where you get the orthogonal directions and you change your direction every time would be like that. So we see here results of the order of 10 to the 5th, right? Like a square root of condition number.
Right.
So that's something we haven't thought about it. I was just thinking loud now.
That's really good point. I haven't thought about.
Because I mean, if you think about gradient descent versus conjugate gradient descent, that's what, you know, because conjugate gradient descent also for the problem that you know, if you didn't have a round off and so on, then there's the theorem, right? Chingolo, infinite number of iterations, you can prove that you finish you converge with conjugate gradient descent, unlike gradient descent. And that's what you also show in the previous example.
Right.
So there is some similarity here that we didn't exploit, actually, I think.
Yes, I agree. This is Jerome. I totally agree.
Yeah, actually, that's a really good point.
Jerome, you think it's related?
Yes, I mean, I talked with Yeonjong about that. I wanted to mention him the conjugate gradient, but I still believe there are some differences because conjugate gradient is based on Krylov spaces, and I don't think we have the Krylov spaces. Still believe.
Yeah, no, that's right. Yes. But we can investigate that, right? If there is indeed such a dependence, and then
you must.
Yeah, you must. Yeah. Okay.
Yeah, that's a really good point. Let me do some run test and see for this specific example which one is and the convergence behavior of the conjugate gradient. And actually that's a really good point. Okay, let me continue. So this is a function approximation example. So we consider the three test functions, the oscillation function and some smooth function and discontinuous function. And we consider the two-layer neural network with the tanh activation function so that our number of the parameters is 3 times n. So this is in optimization perspective, this is a high dimensional problem. And we are just minimizing the square loss. And this is the example for the result of the first test function. We use the 10 quadrature point at the moment. And here I compare with the gradient descent. And for many other configuration of our adaptive terminal Caputo fractional gradient descent. Then you can see that for various setups, actually Caputo fractional gradient descent performs a lot better than gradient descent. And for these examples, we don't know what is the optimal learning rate to be used for the training this A1J and A2J so that we do some brutal force the line search so that we create the 32 grid ranging from 10 to the minus 8 and 10 to the minus 1 and choose the best one that decrease the smallest loss value. So this test is only relies on which method find a more good descent direction rather than how we find the optimal step size, because everything is optimal in terms of the step size for the internal the weight in the A1J and A2J. We might not get optimal one, but we do some solid line search, the grid search, so that we believe that this is the somehow so we just want to rule out the choice of the step size is out of issue, just focusing on the which direction is better. Then you can see that gradient descent, we do the better than gradient descent consistently for various situations, for various choices of gammas. And this is for the test case 2. And in this case, you may see that the gradient descent also doing a good job because the function is easier to approximate. And this is the discontinuous function example. And you can see that our method is consistently outperformed that gradient descent. And not to mention that all the result produced by our the Caputo fractional gradient descent actually produced a good generalization performance at the same time of the minimizing the loss in all of the examples, as you can see here, dashed line. The dashed line is I'm just producing the mean square error on another set of the 10 to the 5 data point. And now let's investigate the performance with respect to the number of the quadrature points. So previously I used the 10 quadrature points so that, to be fairly speaking, we are 10 times expensive than gradient descent. Then what happens, we use the smaller quadrature points. So here is the result. So we actually tested from the S is the number of the quadrature point. Actually, in the paper, we tested from S equal to 1 through 10, but I'm here just to show 1 through 5. That's good enough for already. And you can see that even though we use just one single quadrature point, which is the computational cost is the same as the gradient descent roughly, we see the better convergence and good generalization performance as well. And similar behavior is keep observed for the other case. And in this particular case, for some reason, by using one single quadrature point actually performed the best. And the blue one, computational cost of blue, is roughly the same as the computational cost of the black, which is a gradient descent. And the similar behavior is consistently observed in this case as well. I forgot to change this graph, but this is a discontinuous function.
Can I ask a quick question here, Yeonjong? So
yeah,
I believe alpha is the order of the fractional derivative that you have, right?
Yes.
So do you tune this parameter?
No, I just randomly choose some random number I feel like to use, but I tried a couple of different things, but I don't see the big differences.
Okay, interesting. Okay, thanks.
Can I ask a question?
Yeah.
So, sorry for my stupid question, but how do you choose the kernel of your fractional gradient descent? I meant that why are you choosing? You are introducing a specific fractional gradient descent. So how do you choose this kernel? Is it Caputo? You said that's a Caputo derivative. Why not, for example, you are considering tempered Caputo or other kernels? My question, concerns with the applications. Is there any is your kernel related to the data you are using, or you just pick it and you are testing and without any relation with the data you are using?
I think that's good question, but I don't have a good
answer. Mehdi is asking why the Caputo derivative, why not another definition of derivative? And yeah, I think it has not been explored. People have done this before. Some people use variable order, and this is what I had suggested to Yeonjong, variable order. But some people did a variable terminal instead of variable order, and the results were kind of not similar. So but there was no systematic selection of the kernel like you are suggesting, Mehdi. That has not been done yet. That's the answer.
Okay.
So it's not clear, for example, if the tempered fractional derivative with finite horizon, right? Okay. For example, the non-locality will be limited somehow by the extra parameter. That could also be useful. It's not clear yet. Not been tested yet.
I was thinking that if the kernel is related to the data we are using, so you can choose the kernel according to the data. It's not, independent. But thank you for the information.
Yeah, I think that's a good question, but I think let me illustrate the point where I skimmed through this adaptive order part. So based on how we choose the fractional orders perspective, actually what I derive is actually it's not that sensitive to the choice of alpha k, beta k, rather than how it converges to, like whether this order converges to 1 or not. But how specific design should we use is a little bit unclear, and a couple of people introduced various some suggestions in their own papers, but it is unclear whether that is the truthful general problem, so that we don't have any systematical way of proposing how we tuning the fractional order or smoothing parameter, etc. And as you mentioned that I think it should depending on some physical context or some of the locality has to be blended in, then that might give you better understanding or better design of integral terminals or fractional order or further smoothing parameter. So that's why we propose the generic framework, because there are so many things to be tuned. And specific choice that leads to the better result is the new method, basically, from our perspective. So,
okay, thanks.
And the reason that why I started with the Caputo fractional derivative, that's my personal choice, to be honest. I found the Caputo fractional derivative is more, okay, because this is my first work on the fractional field, and my background is math, and from mathematical perspective, I like the Caputo fractional derivative better. For whatever the reason is, the definition is cleaner and expansion is natural to me. And furthermore, it has a continuity from the left, so that I can well match to the, because for me, if you take a derivative of constant, it should be 0. And that is somehow well consistent with the Caputo fractional derivative. So that's, but as George said, things can be more explored. Has not been done yet. Yeah.
Can I ask one more question?
Yeah, sure.
So did you try Riemann-Liouville derivative or not?
No, not at all.
No, he just told you, Mehdi, he just said that he wants the constant to be 0. Okay. The derivative constant to be 0. So that will exclude that. And intuitively, Caputo derivatives, of course, are being used for initial value problems. That's where the big success is. And if you think about it here, if you consider time as iteration, it does make sense what Yeonjong.
I understand it, but I was wondering if we could use Ritz derivative, because in the limit, I mean, boundary limits, we can generate integer order, and we can see the difference between an integer order gradient descent and fractional, because you're saying that fractional parameters doesn't change at all. So how about if we use a derivative that in the boundaries, it converts to an integer order, like, for example, Ritz derivative in 1D. I meant that, you know, for example, fractional Laplacian, okay? For fractional Laplacian, in boundaries, it goes to integer order derivative. I was thinking that, how about using that fractional Laplacian here, okay? And then in limits, it goes to integer order. Then I would like to see how fractional parameters can change. You're saying that they don't change the result at all, but how about that case for fractional Laplacian? We know that when alpha equals 1, we can generate an integer order Laplacian. I was going only to, I mean, check the difference between these cases. That's only out of curiosity.
If I add a comment here, I think even Mehdi, for this case, if alpha goes to 1, this actually also recovers the integer order case, if I'm correct. Because the Caputo recovers the integer order fractional as alpha goes.
So then the fractional parameters should show some differences in some ranges. I mean, like for example, when you are getting close to integer orders, you should regenerate the normal gradient descent.
Okay, so that's a good question, but that is not true in this specific case unless beta k is 0.
Okay.
Because if alpha k equal to 1,
okay,
then this creates the, okay, then this is becomes the second order.
Okay.
And I think there's some singularity occurs because during this derivation, I assume that alpha is always below 0 to 1. And if getting equal to 1, then some term becomes 0, so that this equation does not hold anymore. So that the main principle of this formula actually goes back to the one-dimensional equation here. And when alpha equal to 1 exactly, unless beta, so this is a special case, beta equal to 0. When beta is not equal to 0 and alpha equal to 1, then there's some singularity occurs during the derivation. So that in the limit sense, actually, that the second term actually plays a big role here. So so this term, 1 plus alpha k.
I think your quadrature points are not valid anymore either, because the integral that you're computing, it becomes.
Yeah, that's right. Quadrature doesn't work as well. Yeah, of course.
Yeah.
So I was wondering if in limits, I mean, for example, not exactly 1, but very close to 1. But I got your point.
The one thing I noticed that if you trying to use the fractional order and design optimization and trying to tune your fractional order,
okay,
then theoretical result, I'm not sure the empirical one, but theoretically what you can show is at best, your method is at best as the gradient descent, because you're trying to mimic what gradient descent do, is essentially. So that turns out to be no better than gradient descent, even though you spend a lot of work on trying to mimic gradient descent, but does not work.
I see.
Better or not. So that's my intuition. I read about some couple of papers, and that was my first approach. And trying to somehow mimic the fractional order, trying to get the right angle. But it does some okay job compared to the fixed fractional order, but no better than gradient descent at all eventually. So yeah, so I hope that might give you something. And that is also consistent with my numerical examples, because there are a lot of variation has been proposed, like truncation of approximating the Caputo fractional derivative, or some adaptive terminals and adaptive order and mixture of all these. And yeah, but don't really see some really convincing results that, but of course I need to mention that even though I just showed some fixed order like alpha equal to 0.4, etc. But if I change the orders, the curve is certainly different. But what I'm trying to deliver here is actually the general picture does not change much. And some alpha might perform slightly better or slightly worse, but generally the curve looks like this. So I actually tested the various cases like alpha 0.1 through 0.9, and nothing really significantly changed or dramatically ruined the picture. So I didn't bother to show some specific values on that. Yeah.
Thank you. That was very helpful. Thanks.
So this is a summary, my last slide. So we propose a new Caputo fractional derivative-based algorithm for optimization. So from the generic formulation, we propose the 3 versions. I would say that is more motivated by, all right, then what if all those are constant? That is the non-adaptive case. And with the goal of finding the right stationary point of the original problem, we propose the adaptive terminal and adaptive order. And in theory, the adaptive order has a potential to converge to the right thing, but we don't know exact specific sequence or order generation, or how fast order has to increase to 1, or how the smoothing can be goes to something, etc. So many things are to be addressed for this one. But at the moment, we found that adaptive terminal perform way better than anything else compared to the gradient descent. And especially for solving the linear quadratic problem and ill-conditioned problem, we show that it's quite effective in mitigating the condition number in the rate of convergence. And I would need to mention that all the result we shown is based on the optimal step size. We try our best to find the optimal step size from the range of 10 to the minus 8 to 10 to the minus 1. And for quadratic case, we know how to choose the optimal step size. So that is not an issue. And the computational cost grows proportionally to the number of the quadrature point for the non-quadratic problem and non-linear problem. However, our numerical examples for neural network actually shows that even one single point actually perform a lot better. So like here, this is one single point example. Yeah, that's what I have prepared, and thank you so much.
All right, thank you, Yeonjong, for your wonderful talk. So is there any other questions or comments?
Can I add something, including Mehdi's question?
Yeah, sure.
Caputo derivative will work as a gradient descent method because it's a version of it's a regularized version of Riemann-Liouville derivative. It doesn't have that much singularity at the kernel. For the gradient descent method, Caputo derivative will work better, I think. But I understand what Mehdi said. If you have bigger singularities, if you try to approximate the data or the function which has big singularities, maybe Riemann-Liouville derivative could work as a gradient descent method, but its computational cost would be huge. I don't think it will. It's a good approach. Caputo derivative will work as a gradient descent. It's a good choice, I think. For now, we don't know later what will be.
Yeah, actually, initially I worked together with the Riemann-Liouville formula at the same time with the Caputo, so that Jerome probably know that in my earlier draft, I wrote some two definitions of Riemann-Liouville and Caputo, and George might see those definitions as well. But later on, I found very, because as a mathematician, I found very, Riemann-Liouville is a good formulation, but it's not very.
Yeah, it's a good formulation, but it has singularities in the kernel. It's a good formulation for singular functions.
Yeah, exactly.
It would be a good approach if you have if you want to approximate to singular functions, but its computational cost would be huge. I don't see a better way to compute Riemann-Liouville derivative rather than the Caputo derivative.
I see.
Caputo derivative is better. The gradient descent.
I see. Yeah, thank you for that comment. Yeah, that's helpful. Yeah.
Yeonjong, if we go back to the third case that you didn't do, the variable order, because the last paper I wrote in that subject was actually very attractive. And there they have a profile. You start, let's say, from alpha 0.8, and eventually it's like an adaptive learning rate that we do in stochastic gradients. And then eventually you get to 1, right? So then you guarantee you will get basically the optima of the integer case by just forcing. Now you're showing here that you actually, with the second term, you are converging to the Tikhonov regularization. So in that case, you would need the beta, the term in beta, right? If you use only adaptive fractional order, would you need the second pair, the one that multiplies by beta, which is what you call smoothing?
Safe to say, for quadratic formula, that wouldn't help. So if you set the smoothing parameter to be 0, and just tuning the fractional order does not help. In the sense that the GD will definitely converge a lot faster than fractional order part. So actually the smoothing actually one of the key component for the, from my perspective, the smoothing parameter is one of the key components that handle the huge success of our experimental result. At the moment, I see that fractional order has to come into the play when we try to solve nonlinear problem. For linear case, everything is clean and clear so that we understand almost everything. That doesn't help too much for us in terms of the finding the right fractional orders. But in terms of the nonlinear problems where we have to resolve to solve some quadrature or estimating the fractional gradient, actually that is something going on, the role of the fractional orders. So I think that if the adaptive, go ahead.
Yeah, no, you may remember in the proposal, I had this plot that shows how the, let's say, you get stuck in a certain minimum, right? But by changing the order, you get out of that minimum because you're continuously changing the order, so you never get stuck to a minimum. Now, of course, that does not guarantee you'll get to the correct minimum unless you eventually get the alpha to go to 1. Remember that plot? So I think that's still a very powerful for the nonlinear case, like you said.
Yeah, exactly. Yeah.
The third approach, I think it's very powerful to use the variable order. And then the question is, how do you choose the profile? Like you said, the alpha as a function of time, of the number of iterations. Now we have to asymptote 1, and we know that alpha has to be less than 1. And the question is how fast you. But there may be some parameterization, some theory, but that the important thing is not to get stuck in a local minimum. And that was this guy was showing that I forgot the paper, the most recent paper on fractional order, when he was using variable order. That he had a very nice plot. I put it in the proposal because he had like how with just changing the order you never get to the same minimum. So naturally you get out. Usually, like Ameya in the Rowdy paper, right? You guys put noise or something like that to the activation function to avoid the trap. Now the variable order would do that for you.
I see.
And then we need to build these directions like you're doing with the smoothing.
Yeah, I agree with you because that's something I also observed in the nonlinear case. So although I think the problem might be well chosen in the neural network case, so everything is smooth, so that maybe we don't see some significant and I wonder, because if I see that some of the papers, they don't really consider the optimal step size, so that it might be, for me, a little bit difficult to see that the effect of the direction part. But Jerome, what do you think?
I think there are two behaviors. One, as George said, when you are far from the minimizer, you want to escape local minimizer. And then when you are in the good basin of attraction, then you want to converge fastly to the minimizer. But there are two different regimes. When you want to escape from a local minimizer, we do not care about the convergence. We want to go in the basin of attraction.
Yeah.
That is the good one. So you have two regimes. That's why it may be confusing. What we do here, especially for the quadratic, we know there is one basin of attraction and we try to go as fast as we can. Same for the neural network. When we're in the nonlinear case and non-convex, you will have the two different regimes. So let's say that, as George said, you send the parameter alpha k to 1, beta k to 0. So you say eventually I will be like the gradient descent, and you are stuck to a local minimizer. And if you want to escape, then you want the opposite. Alpha k to be small, beta k to be in greater, to be closer to 1. and you want to have the effect of the non-locality to escape the local minimizer. But it's qualitative, I mean, the way I see it.
But Jerome, so maybe we can design a case where even with this, right? Because he can, Yeonjong can change the alpha.
Of course.
He can,
Yes.
not continuously, but like from time to time, he can change the alpha. But we can design a loss surface where you get stuck for a while, and then we can see how we can use alpha to get out of there. And then when you're going closer, this method is very good when you go closer, right? If you are locally, you have a quadratic loss, nice, looks like a nice ball. Then this, so something like that.
Yeah. I think actually when we change the order alpha k, we also change the smoothing at the same time. It's the couple, I believe, alpha k, beta k, where we have this. And so it would be like, I don't know, it makes me think of reinforcement learning. I mean, either you want to converge and you want to explode, right? And then you have those strategies.
Yeah.
But can I add a comment to this conversation? So isn't it like the second term that you have is like the momentum term in the Adam optimizer? Isn't it? Like
that's a good observation. Actually, we didn't put our method in that manner, but for example, for easy case, if you can think of CK is your previous iteration, then this may look like momentum method, but slightly different momentum method, because you usually have a momentum term which is a constant, but this is a diagonal, so that this is one can argue that, wait a minute, this is a momentum method. Then we don't have nothing to say. You're right, this is you can view as a momentum method, but we derive it from fractional Caputo derivative. So that is one way of thinking. So that originally what I written out is something draw some connection to the momentum method, but I think that is initiate a huge discussion, so that didn't bother to add it. And also this is a generic formula, so that if you choose CK to be a constant, then this is not a momentum. And if you choose the CK to be related to the XK, the previous iterations, then that's momentum. But this allows you to choose the CK to be like some L times the previous thing. Then that is not exactly what people refers to momentum in the community.
Yes,
so,
but I think, this is exactly what we refer to when we talk about like in a local derivative, like fractional. So I wanted to take this offline with you, but now that you brought it up, maybe I ask. So here, when you compute the derivative, the lower terminal of the fractional derivative is the previous step, right? So CK is the previous step in the iteration that you have, if I understood correctly.
That is one version, yes.
This is the one version, right? So basically in each iteration that you're computing the fractional derivative, so from the current step, you only, by computing the fractional derivative, you just go back to the previous step, not all the way to the initial guess that you had. So I think we discussed this before, if you remember, Yeonjong. So I had this question before as well, but I mean, in that setting that you have, in this setting, your lower terminal is the previous step. So I know that you're still computing the fractional derivative, but I was not sure if it is actually the concept of a history in the iteration that we have using a fractional derivative. So this is one comment. So and when you add the momentum term, which is the value from the previous iteration. So now that if we compute the fractional derivative all the way to the initial guess, so it's like that we have we are carrying the momentum term from the very beginning all the way to the current step that we are. So it's like so many momentum term with weighted momentum terms actually. So this is another way to view it, I believe. And then in that sense, to me, it makes sense to use a truncated kernel, like other things that we were just talking about, not only the Caputo fractional derivative, to truncate your kernel at some point. So you don't want to go back all the way to the initial guess that you have. You just want to consider maybe the last few iterations to compute the history. Yeah, so I think this is just one comment that I wanted to make regarding the conversation that we had.
Okay, thank you.
Is there any other comments or questions for the speaker?
Yeah, good discussion. We should have more fractional talks here. Lots of people are interested in fractional, and I think we'll have to resurrect the.
Yep. If there's no more comments or questions, let's thank our speaker again. So, so everybody have a good weekend.
Yeah. Thank you, Min Lang. Thanks for hosting.